Hello everyone. Uh, Welcome to the control system subject. That is, today we'll be discussing regarding the stability analysis using Rootlocus. So, as we had studied previously in the regarding the um, root stability analysis. So, what exactly is the difference between the root stability analysis and the Rootlocus is? We were in the previous method we were just by taking the model of the system, that is taking we were just analyzing the mathematical equations whether they would be stable or not. That's it. That was only what we had done in terms of root stability. But so what exactly happens in root locus here is, so if we vary the any parameter, let us take we generally take the gain as a parameter. Okay, so if you vary the gain from the value from minus infinity to plus infinity, how would my system become, whether it will be a stable, from which point to which point this system would be stable, and from which point to which point this would be unstable. So this is what is being um checked by the root locus method. So that is what we are generally studying here is nothing but is the movement of, okay, so the movement of poles is nothing itself is nothing but as what we generally give it as root locus method. So this was given by W.R. Evans in 1948. So which is nothing but just a simple graphical method which in which the movement of poles are expressed in the S plane. Okay, the system is varied from 0 to infinity. Note that the parameter is usually the gain, but the other parameter also may be varied. But but the root locus method, the gain is assumed to be a parameter which is to be varied from 0 to infinity. Okay, so that is how this root locus concept is exactly. So we'll just let you know. So as I had said, we generally take the gain value as the variable, because let us take a simple expression. So we know that the very basic characteristic of equation is that 1 plus g of s into h of s is equal to 0. So we'll take a new system in such a way that I'm taking a new gain, a gain by k. Okay, so what does how does my system becomes now? So it will be 1 plus g of s is equal to 0. So now I have to represent this as 1 plus k into g dash of s into h of s. Okay, so this is how the system would change. So definitely, so this equation is now depending upon the value of k. So that is what is nothing but is the gain value. So this gain value is varied from all the way from minus infinity to plus infinity. Okay, this k is generally taken from minus infinity to plus infinity. So if it is varied from 0 to plus infinity, we call it as a direct root locus. Then if it is varied from minus infinity to 0, then we call it as an inverse root locus. Okay, so this is what one has to understand while calculating the understanding the root locus point. So generally root locus is nothing but as varying from minus infinity to plus infinity, but generally we study here only from 0 to plus infinity. Okay, so let me take a simple example here. So I have considered a unity feedback system with a g of s as k by s. Obtain its root locus. So 1 plus g of s into h of s is equal to 0, h of s is equal to 1. So substitute it. So g of s is equal to k by s, h of s is equal to 1. Fine. So if we take, so what would be my new root will be? So s equal to minus k. So what is happening here? So if I substitute k is equal to, so let us try to get its root locus. So k here, s equal to minus k. So if I take k value is equal to 0, so my s would be minus k. So what is exactly happening? So the root locus, whatever we are putting the values of k, so it is all the values are turning out to be in the s plane negative axis. So what is happening is, so it is, so minus k values. Okay, so we are getting this side. So as we had so this is what is the nothing but is the root locus. So get so this root locus is nothing but as this is whatever we are seeing in this negative axis. This whole thing is nothing but is your root locus. But we have to understand that why generally we take it as a only from 0 to plus infinity is because of this sort of equations, because whatever the values we get, it will be in terms of generally in terms of negative. So what happens is the stability can be measured here. So if you can see here, all the anything that is in the left side of the s plane is nothing but is said to be the stable one. If the values goes to this side, okay, to the right of your s plane, so then we generally say it as a unstable one. So we can say that this root locus whatever we have attained here, so is nothing but simple stability. Okay, so we have further we call it as an angle and magnitude condition. So how this is checked, we have to see here. So for a general closed loop system, the characteristic equation we know it as 1 plus g of s into h of s equal to 0. So g of s into h of s is equal to minus 1. So as s plane is a complex, we can write the above equation as what, minus 1 plus j of 0. Yes, so all s values can be expressed in terms of what, sigma plus j omega, right? So if you compare, so s would be, your sigma will be minus 1. Okay, so this is what it is. So for any value of s, if it has to be on the root locus, it must satisfy this equation. So if it has to be obey the root locus, it has to undergo, or it has to follow this equation. Okay, this must follow this type of equation. Okay, let us try to see angle condition. So g of s is equal to h of s is equal to minus 1 j0. So if we equating both sides, if you do it, so we'll take the angles here. So I can write this as this form as plus or minus 2q plus 1 into 180 degree. So where q is from 0 to 1 2. So if you say that, so key point here is that minus 1 plus j0, one angle plus or minus 180. Okay, if you take the angle of this, okay, but the point is here minus 1 plus j is a point on the negative real axis, yes, which can be traced as a magnitude as 1. Yes, because when we take it as modulus of it as 1, it will be, so, and an angle will be of what, plus or minus 180 degree. Okay, this this may be from this side if you take it as plus 180 degree, and if you take this as it's a minus 180 degree, so it can be 1. So we generally give it as 2q plus 180 degree. Okay, where q is from 0 1 2. Okay, so the angle condition as can be stated as, for angle of g of s and h of s, for any value of s which is on the root locus of the equation, so this must meet this, that is plus or minus 2q plus 1 into 180 degree, where q is equal to 1 and 2. So if you substitute q equal to some, let us say at the first one 0, so it will be 1 into 180 degree. So if you take the put the next one 2 into 1, so it will be 3 into 180 degree, it will be 540. So what we can just generally write it as, it should be an odd multiple of 180 degree. Okay, so this is what is the condition, angle condition. So we'll just try to show you here with a simple example here. Consider a system with g of s into h of s being given k divided by s plus 2 s plus 4. Find whether this g of s whether s equal to minus 0.75 is on the root locus or not. Okay, we have to check whether the given root is available on the root locus or not. Okay, so what do we do? Let us begin with this angle value, that is angle condition. So that is g of s into h of s at point s equal to minus 0.75. So we have plus or minus 2q plus 180. Q is from 1 to 2. So substituting 0.75 in terms of g of s. So first we have this main equation. So substitute this value in here. Okay, s equal to minus 0.75. So substitute it and get the value. So what do you get here? So just try to check it out here. So okay, so for this the angle would be 0, for this the angle would be 180 degree, for this angle would be 0, and this would be 0. Okay, so anything with minus you are getting it as 180 degree. So obviously the values which is turning out to be minus 180 degree. So that is g of s equal to minus 180 degree at s equal to minus 0.75. So this satisfies the angle condition, and we can say conclude that s is equal to minus 0.75 is on the root locus. In a similar way, if we let us test for s equal to minus 1.j4. For the same case, if I try to take with minus 1 point plus j4. So if we take this, so take the same method. So k plus 0. So next would be s equal to minus 1 plus j4. So here also it is minus 1 plus j4. So this will become minus 1 plus 1, it will be 1 plus. So then if this will be 4, s plus 4, right? So it will be, as it is minus 1 already, it will be 3 plus j4. So now if you take these angles, so you are getting some minus 233.1.23. So what is that, this angle? So this is not at all an odd multiple of 180 degree. Hence we can say that it is not satisfying the angle condition. The point minus 1 plus j4 cannot be on the root locus of the given system. So this is what we can say, whether this is on the root locus or not. Okay, so similarly in case of magnitude condition it is also same. So the g of s and h of s, if you take it, so the magnitude condition should be equal to 1. So if this thing satisfies, so then we can say that this root locus is exists on the that plane. Okay, so key point is that the magnitude condition can be used only when the point is in s plane is confirmed for existence on the root locus by using the angle. So just we not understand that if it is 1, we can directly write it as 1, but if for the existence and all, if you want to do, have to do the angle condition. Okay. Let us see here. We have done one more here. So g of s into h of s being given, s is being given. Okay, the same numerical. If I try to do it, so this is for magnitude of the condition. So substitute it, k equal to, so this all should be in terms of modulus value. So I take s equal to what is minus 0.75 modulus 1.5. So the my k value will be, so as all these are modulus, these all will be a plus value. So your k value would turn out to be 3.047. So in this case, what do we understand here is that so if you try to work it out, so this is a cubic equation, but the use of angle and magnitude condition one after other, we decide that for k equal to 0.468. So one of the three roots is located. Okay, so out of these three roots, one is located at 0.75. Okay, for k equal to 0.30468. So the remaining roots can be easily obtained. So this is what it is. So let us not so much get into depth of that. So what are the general basic rules of construction for root locus? So that is what we have to understand. So the root locus is always symmetrical about the axis. The roots of the characteristic equation are either real, complex, conjugates, or combination of both. Okay, therefore there must be a symmetrical about the real axis. Okay, so what one has to understand is rule number one says it's always root locus is always symmetrical about its axis, real axis. Rule number two. So let g of s into h of s is equal to the open loop transfer function p equal to number of poles, number of z equal to number of zeros. Then we can confirm the basic information about the root locus as if p is greater than, let us see here, if p is greater than case 1, p is greater than z, then the number of, what does this indicate? The number of branches are equal to the number of open loop poles. So then n will be equal to p. Okay, so number of branches will be how much? It will be equal to p. So if it is z is greater, then we have to say that number of branches are equal to z. Okay, so this as one has to understand. So branches will start from the location of open loop out of the p number of branches. So z number of branches will terminate at the location of open loop zeros. The remaining p minus branch will approach to the infinity. So what does this indicate is that, so if example is being given here, if p is equal to 4 and z equal to 4, then the number of roots of the root locus branches is how much? Total equal to, if p is greater here, so p is greater than z, so I can just say that p is equal to n. So number of branches will be equal to 4 p. So n equal to p, it will be equal to 4. But number of branches which will be approaching to the infinity will be, that will be p minus z, which is equal to 3. So 3 branches will be approaching to the infinity. In a similar fashion, here also it is same. So I can take that p equal to, it is quite reverse here. So if p equal to 1, z equal to 4, if so number of branches are taken equal to z equal to 4, the number of branches moving to infinity will be z minus p equal to 3 here. So 3 will be approaching to the infinity. So that's it, very simple, vice versa. Okay, what is rule number 3? A point on the real axis lies on the root locus if the sum of the number of open loop poles and open loop zeros on the real axis to the right hand side of this point is odd. Okay, so what does this reflect us? ಏನು ತಿಳಿದಿದೆ ನಮಗೆ ಇದರಿಂದ ಅಂತಂದ್ರೆ, let me take a simple a g of s into h of s open loop transfer function. So k s plus 1 s plus 4 s plus 3 s plus, so let us try to plot the poles and zeros. So s plus 1 s plus 4 is nothing but as here, these are nothing but as zeros. So first we will write this is minus 4 and this is minus 1 here. Then poles s equal to 0, s equal to minus 3, s equal to minus 5. So s equal to 0, then we have minus 3, then minus 5. Okay, so now what is this rule say? Whether this what does this replicate is, let us say I am taking a point from here to here. Let me take from minus 1 to 0. Okay, if I want to understand this between this gap, okay, minus 1 to 0. So if I keep this point here, okay, from here to the right hand side, ಈ ರೈಟ್ ಹ್ಯಾಂಡ್ ಸೈಡ್ ನಮಗೆ ಎಷ್ಟು ಅದಾವಲ್ಲ ಪೋಲು ಮತ್ತು ಝೀರೋಸ್ ಎರಡನ್ನು ಎಡಿಟ್ by adding poles and zeros. So if the number is odd, then we say that it's a root, it is lying on the root locus. Let me say, so from this point, so I can say that to the right side of this, so how many it is there? It is 1. Okay, so hence number of poles and zeros is equal to totally, here it is 1, so it is an odd one number, so hence this is a on the root locus. So let me say take it on the point, if the point is here. Okay, so to the right side of this, how many points are on the root locus? How many points are to the right side? So pole 1 ಇದೆ, 0 ಒಂದಿದೆ, so 1 plus 1 it will be 2. So how many it will be? 2 numbers. So 2 is an even number, so hence this is no, this is, there will be a no root locus in between this. Okay, on this line. Okay, similarly move it to this side. Okay, so further it will be 1 2 3. So yes, there will be a root locus presence, will be, there will be a root locus. Okay, no root locus, then root locus. Okay, so this is how it is done. A similar sort of example also may be taken here. Okay, so first we will try to plot the zeros. S equal to -2, s equal to -2, I have done it here. 0 I have to keep it as, yes it is there, s equal to -2. Next is s square, so s square it is 2 0, so 2 poles it will be, because it is a s square element, so it will be 0 will be 2, so we have taken 0, 2 elements here, 2 roots we have taken here, and 2 more roots has to be calculated here. So this will be -1 plus or minus j, so -1 here, plus or minus j root 3 minus j, so we have taken here. Okay, there is one more -3 here. Okay, so totally we have here, the rates are being specified here. So now now we have to calculate once again. I have to check whether from between this, let me take this side. Okay, so now if I want to take from this point now, okay, I hope this point mouse cursor is visible to you. So from this point, from this onwards, so between this, let us try to check how many poles or zeros are there. So we have 1 and 2, so it is even, so hence what do I can say, there is no root locus. Okay, similarly come to the next point. So between this also there is, so this is not there exactly, so he has, this is -1 plus or minus j, so -1 is here, -1 plus or minus j it is. For reference they have taken it as -1 here. Okay, so how many it is from this point it is, so 1 2 3 and 4, once again it is even, hence I can write this as there is no root locus. So further you take this side, so how many are there here? 1 2 3 4 5, so the total sum of poles and zeros will be equal to 5. So hence I can say that it will be a odd odd addition, so it will be a odd value, so hence I can say that it says a root locus. There will be a root locus existing here. Excuse me. So what is the key point here? So this rule should be applied to the actual open loops and zeros. The rule should be applied to the sections in between them. Similarly, the complex conjugate or poles or zeros occur in the pair and hence do not affect the condition of the sum. Hence complex poles or zeros need not to be considered while applying this rule. Okay, so because why does he say is that complex conjugates will definitely be, there will be in two equations, so hence it will be nowhere reflecting the system, because it will be, once again it will be an even value, so there is no need to take or consider this complex conjugate. Even then if you consider also, it is well and good, because there is nothing much happening to the system. Okay, so this is what is rule number 3. Now what is rule number 4? Rule number 4. So what does this rule number 4 generally say? So generally the number of poles are more than the number of zeros. So in such case p minus z branches will approach to the infinity. That is what we have already discussed. So this rule gives the information about how these branches approaches to the infinity. So to from which point or so and from which angle does these branches move towards to the infinity. So the branches which are approaching to the infinity, so they move along in a straight lines, so which are called as asymptotes. So asymptotes of the root locus. So these asymptotes are the guidelines for the branches approaching to the infinity. The angle of such asymptotes are given by, so this asymptote angle is being given by theta, which is equal to 2q plus 1 multiplied by 180 degree divided by p minus z. Okay, so this is how the asymptotes angles are calculated. So we'll try to understand this by a simple example here. So let me take, I have this g of s equation, k divided by s plus 1, s plus 2 plus 2j, s plus 2 minus 2 j2. So calculate the angles of asymptotes and centroid he has asked you. So number of we know that number of poles is equal to how many we have here, 1, 2 and 3. So we have poles equal to 3 and 0 is equal to nil we have. So number of branches will be equal to 3 here, p n equal to p, which is equal to 3. So number of branches approaching to the infinity will be p minus z is equal to 3. Poles are located at minus 1 minus j plus or minus j2. The angle of asymptotes are given by theta equal to 2q plus 1 180 degree by p minus z. So it is very clear that, so q equal to, so q, go on substituting with the q values. So we have q equal to 0, so theta 180 divided by, it will be 2, if I substitute q equal to 0 here, be 180 degree divided by p minus z will be equal to 3, it will be 60 degree. So similarly, next if you q equal to 1, so it will be 3, 2 into 1, it will be 2 plus 1 here, it will be 3 into 180 degree divided by 3, so it will be 180 degree. So similarly q2, if I do it same way, so it will be 300. So this is how the asymptotes degrees are calculated. Its centroid is calculated by, that is sum of real parts of the poles minus real parts of the zeros divided by p minus z. So real parts of the poles are nothing but here, I'll come back to that point later. So real parts of where are minus 1 here, so that is minus 1, and real part of the other one is minus 2 and minus 2 times we have, so that is, there is negative real parts of zeros, it is not there, 0 part, so divided by 3, so it will minus 0.1.67. so this is how the angles are being drawn. So we take it from centroid value as minus 0.1.67. From this value, so does your asymptotes move. So one is from 60 degree, the other is from 180 degree, okay, the other is from the 300 degree, okay. So this is how the asymptotes move. Yeah, I forgot to add the fifth rule there. So that is what is the getting the break, what was that, getting the centroid, okay. So the rule number 6 says that these are nothing but as what are the values that are moving infinity, right? So we called them, we have their points called as breakaway points. So what do we is that, how it is calculated, we'll see here. So breakaway point is a point on the root locus when multiple roots of the characteristic equation occurs for a particular value of k. So let us say g of s equal to h of s, k divided by s plus 2. The root of this equation will be s equal to minus 2 and s equal to 0 here. When such two or more roots of the occur, so the k is called the breakaway point. So the root locus branches leave the breakaway points at an angle of minus 80. They move, they divert in such a way that at an angle of plus or minus 180 degree and divided by n, where n is the number of branches approaching at that breakaway point. So how to calculate the how many number of branches, we'll see there. So as breakaway point indicates the value of multiple root, it is always on the root. So we'll take simple example here how this yeah. So general how to predict the existence of breakaway point. Okay. Let me take g of s. If first case is that if there are adjacently placed poles on the real axis and the real axis between them is a part of the root locus, then there exists a minimum one breakaway point in between the adjacently placed poles. So what does this say? If there are adjacently placed poles, okay, if there are two adjacently placed, one after the other, if there are two poles, if they are placed, okay, so then they will have minimum one break point. Okay, so they will have minimum one breakaway point, but it should be lying on the root locus. So this value should be on the root locus. As I said, how to calculate the root locus and all, we have seen it. So if I want this area to be root locus, or we have to check it whether from this side it should be odd value, that is summation of poles and 0 should be odd value. Okay, then it will be on the root locus. Yes, I can see here this is a if I take from here, it will be only one value, so hence this value is on the root locus. Yes, now what will happen? So this value is on the root locus, and hence and also there are both the poles are on the root adjacent, and there will be definitely a minimum one breakaway point. Okay. Let me take the next case. G of s equal to k into s plus 6 and s plus 2. So this is what is being given. Try to plot it. So this is s equal to 0. Here we have poles s plus 2, s plus 4, minus 4, minus 2. So what I can see here, these two are adjacently placed. Fine. This is on the root locus because from here it is odd. Yes, it is on the root locus. This has a breakaway point. Okay, they are adjacently placed. But if you look at this here, these are also adjacently placed. Okay, this is also adjacently placed. But still, it is what we can say that this value is not on the root locus. How can I say? This will be 1 plus 1, it will be 2. So 2 is an even number. So hence I cannot this value. This part doesn't lie on the root locus, so hence it's a not root locus. Okay, so hence there will be no existence of breakaway point. Okay, so this is what one must understand. So this is how it is predicted. So second case, what it says, if there are two adjacently placed zeros on the real axis, the section of this real axis, it is quite similar to that. So only there we studied regarding it was the previous case, it was regarding poles. Now it will be same method, only if two adjacently placed zeros are there. Okay, so and one more thing you have to understand here. So these when these are poles, when these are poles, you can see there is this points are moving in. Okay, these breakaway, they are moving away from the, these breakaway points are moving away from the breakaway point. Okay, so this is what is you have to understand. Okay, if this is 0, it will be moving away. If this is a pole, it will be moving in. Okay, so this is what we have to understand. We generally call it as such points, we call it as break-in point and breakaway point. Okay, this we have to understand. So there is one more case, is that there is one more last one, is that how to find out the breakaway point. If there is a 0 on the real axis to the left, okay, if there is a 0 on the to the left of 0, there, if there is no pole or a 0 on the existing real axis, and the complete real axis to the left of 0 is a part of the Rootlocus, then there exists minimum one breakaway. So what is that is, from this point, okay, to, if it is the 0 is on the extreme left, and this path should be a Rootlocus path. Okay, then if it is so, ಇಲ್ಲಿ ಎಷ್ಟಾದರೂ ಇರಲಿ, to this may be anything, any number of poles or anything. Okay, these may be poles or zeros, but if this is on the Rootlocus, if this value is on the Rootlocus, then I can say that there will be a minimum one breakaway point to the on this left hand side. Okay, so that is one more way of checking it. Okay, this is one more value of existence of breakaway point. Now now steps to determine the coordinates of this breakaway point. How to get this breakaway points coordinates? There are these steps to be dealt. Okay, construct the characteristic equation 1 plus g of s equal to 0. From this equation, get the value in terms of k, in terms of f of s, then differentiate dk by ds and equate it to 0. Then roots of the equation you have gives us the breakaway points. Let us try to, if there are there is a simple example exercise being done here, we'll try to get here. So the characteristic equation is being given. So 1 plus g of s into h of s equal to 0. So get this in the form. So we have this one, g of s into h of s is equal to 1. So take this value, equate it to 0. Then step 2 is equate to k value, get in terms of k, we have taken, differentiate that value with respect to s and equate it to 0. Then 3s square plus 10s plus 4. Therefore breakaway points is equal to, find its roots. So if I find roots, it will be having s equal to minus 0.46 and minus 2.8. Substituting the expression for k, if you substitute here, so I will be getting positive value here. So these are what the breakaway points. Okay, so for s equal to minus 0.46, if the value is positive, so s equal to minus 0.46 is a valid breakaway point for the Rootlocus. If it is getting the negative, so that should not be considered. Okay, if the k value is negative, then it should not be considered. Okay, so hence I consider this as at minus 0.46. So this is value is valid. So the point at which the angle is leaves the breakaway point is 180 degree plus or minus by n. That is number of branches approaching will be here, how many, from one from this side and one from this side, it will be 2. So it will be plus or minus 90 degrees. So it will be moving in this way. So breakaway point will be moving this way and this way. Okay, this is how it is. It is rule number 7. So rule number 7, the intersection of root locus with imaginary axis. So this can be determined by the following procedure. The step 1 is consider characteristic equation 1 plus g of h is equal to 0. So this is as obtained in rule number 6. So construct its roots array in terms of k. So determine k marginal value, that is k which creates one of the rows. Yes, the process will be explained in next numerical. Construct auxiliary equation A is equal to 0 by using the coefficient of row which is just above the row of zeros. So fifth step is roots of auxiliary equation A is equal to 0 for k equal to k marginal are nothing but the intersection of points of the root locus with imaginary axis. So we'll try to see how these are explained, the simple numerical. Let me say this is my g of s, h of s, okay. So k divided by s plus 1 into s plus 4. The characteristic equation is being given by 1 plus g of s into h of s. So this I can solve it and I can write it as s cube plus 5s square plus 4s plus k equal to 0. So roots array further. So we know how to calculate this roots array. So let me know we have odd ones written first. 1, 4 as it is, 5, k. So let us assume this k, we'll calculate it here. So yes, this is what is my roots array now. Okay. So how do I calculate this k value? So always, so for the existence of the system to be stable, all this k value should be greater than 0. Yes, it should be a positive value. Okay. So this k should be equal to greater than equal to 0. That is so let me come from here. So here this is what is 20k divided by 5 equal to, yes, so this is what I have taken, corresponding k margin equal to 20 for the existence. This should be, so if this is has to be 0. Okay, so 20, that makes the corresponding row s1 to as row of 0. So this will become 0. Okay, 0 by 0, 0, 0 agudate. So that's what we have to do it. So if this k marginal value will be 20, then we take the above equation, that is s square. So this equation we are taking it as 5s square plus k equal to 0. K is equal to k margin equal to 20. So if you take that k margin value equal to 20 over there, we will get our root as s square equal to what? Minus 4. Okay, so we'll get s square equal to minus 4. Therefore we have the roots as s equal to plus or minus j root 2. So I can say that, so s equal to plus or minus j root 2 are the points of intersection of root locus with imaginary axis. Okay, so if k margin is a positive, there is a valid intersection of root locus with imaginary. Okay, so such problems are, so these problems are already previously we have already discussed. So key point is that if k margin is a positive, the root locus intersects with the imaginary axis, but if k margin is a negative root locus does not intersect with imaginary axis and lies totally in the left half of the S plane. So that is what one has to understand. So what is next is rule number 8. Yes, it is the angle of departure at complex conjugate poles and angle of arrival at complex conjugate zeros. So these are calculated only when we come across with complex conjugate poles and complex conjugate zeros. So we have to calculate this angle of departure and angle of arrival of complex conjugate poles and zeros. So let me take the first one, the angle of angle of departure of our complex pole. So this is angle, so how do we get this? Phi d is equal to 180 degree minus phi. Okay, so where phi is nothing but as summation of phi p minus phi z. Okay, summation of phi p minus phi z. So what is this phi p and phi z are nothing but as the contributions of angles made by the remaining open loop poles at at which the phi d is to be calculated. So it is nothing but the total angles contributed by the poles, and this is the angles contributed by the zeros. Okay, poles and zeros. So this is what is nothing but as a total phi. So phi d is equal to 180 minus phi. So this is what is nothing but as a complex pole. This is for angle of departure at complex pole. Now let me take a simple example here. So calculate the angle of departures at the conjugate poles. So he has asked for only conjugate poles here. So let me take here p equal to 4 we have here, 1 2 and 2 square is 4, so total we have 4, and 0 we have 1 here. So poles are at 0, minus 4, and there is one more is minus 1 plus or minus j. So 0 is at minus 2. So draw pole 0 plot. So if you try to plot it, so 0 minus 4 minus 1 plus or j, minus 1 plus j. Okay, then we have zeros to be drawn. 0 is at minus 2, so this is where it is at minus 2, 0. Let us calculate the phi d first one at the pole. We generally calculate it for complex conjugate poles. Yes, you have to remember that. So let us calculate at phi d at minus 1 plus j. Okay, so this is where we are trying to calculate the phi d value. Okay, so join all other poles and measure the calculate the angles. So we are trying to calculate all these angles. We have one angle is being framed by here, one here is there is one more z1, we can call it a phi z1, phi p2 we can call it as phi p3. So we have to calculate how these angles are made. So these we have to calculate with you using your trigonometric functions. Very simple. They are Pythagoras values. If you apply, you will definitely get the what exactly is this angle. Okay, so this can be dealt very easily. We can do it very easily. Okay, so this is what is the addition of total poles. Okay, that is phi p, that is phi p1, phi p2, phi p3. Then phi z is one, which is the angles contributed by the number of zeros. Okay, so phi pn, what we have got is, by if you try to do it with your trigonometric values, you will definitely get it as 1 using that functions. It is 135, p2 is 90, 118.43. so total you have 243 here. So phi z equal to 45, so add them. Okay, phi equal to, we have this much value, phi d equal to 180 minus this value, we will be having it as minus 18.43. This is for phi d is minus 18.43, for which one? This is for s equal to minus 1 plus j. Okay, similarly if you try to do it for minus 1 minus j, you will get the same angle but with a positive sign, that is phi d. Okay, for the next so this is minus, he is saying minus 18.3. For this point we have got it as minus 18.43. so put a, from this take it as a linear value, so you can draw a line, straight line with an angle making an inclination of minus 18.43. so this is how we have to draw the, when if it is a complex conjugate poles. So similarly if it is, so you can see that this is how it is departing. Okay, so this is how it have to draw. Now angle of arrival is quite same method, but only thing is that it is 180 degree plus phi, but once again the phi will be the same, summation of phi p minus phi z. So the similar thing has to be done for if it is a complex 0 one. Okay, so these are very pretty simple, and we will directly do them in the numericals. So we can also find the graphical determination of k for a specified damping ratio zeta. So let me take I can represent this equation in terms of if I take this side as a minus zeta omega n, if I take this as zeta omega 1 square root of 1 minus zeta square, so this I can write this as roots can be expressed in terms of minus zeta omega n plus or minus zeta omega n square root of 1 minus zeta square. So if I try to take its OP value, okay, that is if I just want to calculate the its theta, so cos theta is equal to what? It's adjacent by 1 is what we know it, so it is minus zeta omega n, yeah, divided by length of this OP. So we have length of OP equal to what? Square root of these both, okay. So if you have to take it, okay, summation of this minus zeta omega n square plus omega n square j omega n square, this value, so this value would turn out to be omega n, okay. If you just try to calculate it, yes, because what will happen is if you try to bring in the volume values, it will turn out to be omega n. Then cos theta equal to zeta omega n divided by omega, so zeta, so theta is equal to cos inverse of zeta. Now it is desired to design the system with a certain damping ratio for zeta, for which it requires to decide the corresponding value of the system gain by using the root locus. So if you want to design such a system with a margin of k value, so you can also do that by varying your zeta value also, okay. So damping issue may be used in order to maintain this. Find out the k value. So general steps to solve the problem on the root locus, so they are pretty simple and straight, what we have discussed till now, all those steps. So step 1, get the information of poles and zeros, number of branches. Second one, draw the pole zero plot, identify the section of real axis for the existence of root locus, whether it is on the root locus or not. And second, and predict the minimum number of breakaway points by using the general predictions. You can predict the number of breakaway points there. Then calculate the angle of asymptotes, determine the centroid, sketch a separate sketch for step 3 and step 4, okay. You have to sketch independently. Calculate the breakaway and break-in points. If breakaway points are complex conjugates, then use, if the roots, if you get them are in terms of complex conjugates, then you have to use the angle condition to check whether their validity as they are valid breakaway points or not. Calculate the intersection of points of root locus with imaginary axis. Then calculate the angles of departure and arrival if applicable. Combine 1 to 7 and draw the final sketch of the root locus. Then predict the stability of the performance of the given system using the root locus. Okay, we'll do a simple numerical on that. For a unity feedback system, I have been given with a g of s. So sketch a rough nature of root locus showing all details on it. Comment the stability of the system. P equal to, by seeing this I can write this as P equal to 3, Z equal to 0. So number of branches equal to N equal to P equal to 3. So P minus Z will be P minus Z is equal to 3. So these three branches will terminate to infinity. Okay. So number of poles we have can calculate it as S equal to 0, minus 2 and minus 3 will be. So place them. So one is here, another is here. Then check for whether the root locus exists between them or not. So if this is here, so there will be a root locus existing from this point. It's an odd value. So if I take this from this to this, if you look at the right side, there is only one pole, so then it is only positive value. It's a odd value, then it will be a root loss exists. So from here it will be 2 1 and 2, so it will be even value, so it will be no Rootlocus. From here it will be 3, so it will be Rootlocus exist. Okay. Now, angle of asymptotes. So as we know that there are 3 branches are approaching to infinity, we must understand there are 3 asymptotes which are required to be found out.